This is the introduction to Experiment 9, Spectrophotometry of Iron-Containing Solutions. The goal is to determine the amount of iron in an unknown liquid sample, which will be provided to you in a 100 milliliter volumetric flask. This will be just like the calcium experiment. You'll take the flask, fill it up, and that will be your unknown. The method you're going to use is spectrophotometry, so no titration at all this time. You're going to make two measurements. One will be an absorption spectrum, and the other will be a calibration curve. Each of these is going to consist of multiple readings of absorptions. In the absorption spectrum, you're going to change the wavelength and keep the concentration the same. You're going to find the wavelength of maximum absorption for your solution. And then when you make your calibration curve, you're going to change the concentration and keep the wavelength the same to find your instrument's response to iron concentration. The indicator that you're going to use is going to be a complex between iron ions in solution and a molecule called 1,10-phenanthroline. This is colorless when it's not complex to iron, and various shades of red when it's complex to various concentrations of iron ions. The instrument that you get is either going to look like this, which is an analog version of the instrument, or like this, which is a digital version of the instrument. The instructions in your lab procedure apply the same way to both. The knobs are the same, the way that you calibrate and zero it is the same for each one. Some people feel like they've been given short shrift when they get an analog instrument, but I'll show you some results later on that prove that this is not the case. In addition to your iron standard solution, which has a concentration of 10 ppm, you're going to need to add these three things to get your solution to turn the correct color. What's very important is that you add them in the order that they're presented in your lab manual. So first you add the hydroxylamine hydrochloride, then you add the 1,10-phenanthroline, and finally you add the sodium acetate. Adding them in a different order will result in poor performance of your solution's color development. The test tubes that you're going to use in your instrument look like this. They look exactly like the disposable test tubes in the lab, except that they have this blue F on them. You should only use test tubes with this blue F in the spectrophotometer, and when you fill them up, you should fill them at least to the bottom of the blue F. Some of them have a white F, and in that case you should fill it at least to the bottom of the white F. One of these test tubes is going to stay filled with your blank. The other is going to be for your different iron-containing solutions. In spectrophotometry, the idea of a blank is that it contains everything that is in the sample solutions except the colored analyte of interest. So in this case, it's going to contain everything except the iron ions. Okay, it will contain the 1,10-phenanthroline, which again, when there's no iron, has no color. When you add your various reagents to the volumetric flasks and give them a little while to develop, this is what you're going to see. On the right is the flask that had 1 milliliter of 10 ppm iron solution pipetted into it. On the left, the darker solution is the one that had 10 milliliters of iron, and in between there's 2, 4, and 5. This is a change from the procedure that was on Blackboard until this afternoon. The correct one is there now, but the incorrect one says that you will have a 25 milliliter pipette to make your most concentrated solution. You won't. You'll have 1, 2, 4, and 5 at your bench. You still also have your 10 milliliter calibrated pipette. So these are going to be your 5 calibration standards. You're going to make your absorption spectrum with the most concentrated one, the 10 milliliter one. So you're going to make your absorption spectrum and you're going to find your wavelength of maximum absorption, which when I did this on my instruments was 509 nanometers. Yours will be different, almost certainly. Once you know that, you're going to set your spectrophotometer there and leave it there, and then you're going to take repeated measurements of your different iron-containing solutions for your calibration curve. I only did one measurement because I was pressed for time, but you're going to do them each 3 times. So these are the results I got with the analog spectrophotometer and the digital spectrophotometer. The equation of the line is not important. That can be different for each instrument. What is important is the R-squared value, and if you notice, they're extremely similar, analog versus digital. So you do not need to be alarmed if you get an analog spectrophotometer. They look older, they don't have a nice digital screen, but they work just as well. So your data analysis. For your absorption spectrum, you're going to do 3 scans with your most concentrated solution. First, you're going to step down from 600 nanometers to 400 nanometers in 20 nanometer increments. Then you're going to find the wavelength of maximum absorption in that scan, go above it by 10 nanometers and below it by 10 nanometers, and scan over that new range 5 nanometers at a time. Then you're going to do a similar thing with 2 nanometer steps. You're going to use all 3 of these spectra together to find the wavelength of maximum absorption, and you're going to set your spectrophotometer there for the next part. So you're going to take that wavelength and you're going to find the absorbance of each of your 5 calibration solutions. You're going to do each of those solutions 3 times, so you have not only an absorbance, but you have an average absorbance with an uncertainty at each solution concentration. You're then going to measure the absorbance of your unknown solution and use the calibration curve equation to solve for the concentration of iron in your unknown in parts per million.